Here's a deceptively simple pattern mastery 100 question that's caught many off guard. Same tree. Top companies love it because it reveals your understanding of recursion and attention to structural detail. Over 20% of candidates miss a subtle base case or comparison. Get this right and you'll have recursion fundamentals locked down for your next interview. Let's master same tree using the basic approach, breaking down the problem, analyzing, structuring a solution, and checking all edge cases. Let's break it down. Given the roots of two binary trees, return true if they're structurally identical and all their nodes have the same value. Otherwise, return false. Input: two binary tree root nodes, P and Q. Output: Boolean: true if the trees are the same, false otherwise. Real-world example. Suppose you're building a cloud backup system, and you need to verify if a backup is a true replica of the original tree structure and content. Interviewers might ask, how would you compare two hierarchical document models for structural and content equality? Let's assess. What's tricky? You have to check both the structure and the values at every node. Recursion is the natural fit. You need to handle all the cases where one tree might branch when the other doesn't, or values don't match. Think step by step. If both nodes are null, they're the same at this branch, return true. If only one is null, the trees differ, return false. If both nodes exist, check if their values match. If not, return false. If yes, recursively check their left and right children. The answer is only true if all these checks succeed for every node. Let's add more. Be sure to check both left and right subtrees. Missing one is a classic pitfall. Order of checks matters. Avoid null pointer errors by checking for null before accessing values. Edge cases. Both trees empty should return true. Trees with same shape but different values should return false. Trees with different shapes should return false. Here is the structure. If both P and Q are null, return true. If only one is null, return false. If both exist, compare their values. If not equal, return false. Otherwise, recursively check left and right children. Return true only if both left and right subtrees are also the same. Let's try to implement it using solution 1. Line highlighted. Class solution. We begin with the solution class. This holds our method for comparing two binary trees. Line highlighted. Public boolean is same tree node P, tree node Q. This method takes two tree roots, P and Q, and returns true only if the two trees are structurally identical and have the same values. Base case checks. Line highlighted. If P equals null and Q equals null, return true. This is our first and most important base case. If both nodes are null, that means we've reached the end of both trees in the exact same place. Since both are empty here, they match. So we return true. Pause. Line highlighted. If P equals null vertical bar Q equals null, return false. This checks the opposite situation. If only one of the nodes is null but not both, then the trees differ in structure. One tree has a node where the other doesn't. So the trees cannot be the same, and we return false. Line highlighted. If P.val equals Q.val, return false. Now we compare the values stored in the current nodes. If P and Q have different values, even if the structure matches, the trees are not identical. So we return false right away. Recursive comparison. Line highlighted. Return is same tree P.left, Q.left, and is same tree P.right, Q.right. This is where the recursion does the heavy lifting. We check whether the left subtrees match, and the right subtrees match. Only if both are true do we consider the entire trees identical. Pause. Time complexity note. We visit each node once, and each visit does constant work. So the overall time complexity is O(n), where n is the number of nodes. Line highlighted. This closes the isSameTree method. Line highlighted, and this closes the class. Final wrap-up summary. And that's how this algorithm works. It first handles all the base cases for null nodes and mismatched values, then recursively checks whether the left and right subtrees align perfectly. Efficient, simple, and elegant. Highlight input box. P equals 1, 2, 3, Q equals 1, 2, 3. Let's test our function with these two binary trees represented in level order form. P equals 1, 2, 3 and Q equals 1, 2, 3. Both describe the exact same structure. 1 is the root. 2 is the left child. 3 is the right child. Explain the logic briefly. Our algorithm checks if the two trees are identical, meaning same structure and same node values. Since every corresponding node matches perfectly, the trees are indeed identical. Highlight output box. Output, true. Expected, true. And that's exactly what we get. True, matching the expected value. The test case passes cleanly. So, our implementation is correct. The algorithm correctly verifies the structural and value-based equality of both trees. Simple, accurate, and reliable. Same tree. Solution 2. BFS. Line highlighted. Import java.util. We import the utility package so we can use queues. Line highlighted. Class solution. We begin the solution class where the iterative comparison logic lives. Line highlighted. Public boolean is same tree node P, tree node Q. This method checks whether two binary trees are identical in both structure and value. BFS initialization. Line highlighted. Q tree node greater than Q equals new linked list. We create a queue to store pairs of nodes that should be compared. Each element is a two-node array representing matching positions in both trees. Line highlighted. Q.offer new tree node PQ. We start by adding the roots of both trees as the first pair to compare. BFS loop. Line highlighted. While !Q. is empty, we process pairs until we've checked all corresponding nodes. Line highlighted. Tree node. Pair equals Q.poll. We remove the next pair from the queue. Line highlighted. Tree node node 1 equals pair 0. We unpack the first node. Line highlighted. Tree node node 2 equals pair 1. And we unpack the second node. Null checks. Line highlighted. If node 1 equals null and node 2 equals null, continue. If both nodes are null, that means both trees have a missing node in the same place. We simply continue, because this pair matches. Line highlighted. If node 1 equals null vertical bar node 2 equals null, return false. If only one of them is null, the structure differs. One tree has a node where the other does not, so we return false immediately. Value check. Line highlighted. If node1.val equals node2.val, return false. If both nodes exist but their values differ, then the trees are not identical. Add children to queue. Line highlighted. Q.offer new tree node node1.left, node2.left. We enqueue the left children of both nodes so we can compare them next. Line highlighted. Q.offer new tree node node1.right, node2.right, and we enqueue the right children. Together, these pushes ensure the BFS continues level by level. Line highlighted. This ends the BFS loop. If we finish processing without hitting a mismatch, the trees must be identical. Final result. Line highlighted. Return true. We return true because all corresponding nodes matched. Line highlighted. End of the method. Line highlighted. End of the class. Time complexity note. Every node pair is checked exactly once, and each comparison takes constant time. This gives the algorithm a total complexity of O(n), where n is the number of nodes in the trees. Final wrap-up summary. And that's how this algorithm works. It first places both root nodes into a queue, then iteratively compares matching node pairs and enqueues their children, ensuring both structure and values match across both trees. Simple, iterative, and elegant. Highlight input box. P equals 1, 2, 3, Q equals 1, 2, 3. Let's test our function with these two binary trees represented in level order form. P equals 1, 2, 3 and Q equals 1, 2, 3. Both describe the exact same structure. 1 is the root. 2 is the left child. 3 is the right child. Explain the logic briefly. Our algorithm checks if the two trees are identical, meaning same structure and same node values. Since every corresponding node matches perfectly, the trees are indeed identical. Highlight output box. Output, true, expected, true, and that's exactly what we get. True, matching the expected value. The test case passes cleanly. So, our implementation is correct. The algorithm correctly verifies the structural and value-based equality of both trees. Simple, accurate, and reliable. Quick recap on same tree. It looks simple, but it's a brilliant test of your recursion fundamentals and your eye for structural detail, exactly why top companies love it. We frame the task as a pure comparison problem. Two roots n, and we return true only if both trees match in structure and in every value. We highlighted why recursion is the natural fit and called out the easy-to-miss cases. Both null is true, one null is false, and any value mismatch fails, plus the reminder to check both left and right subtrees. Our plan was a tight sequence. Handle the null checks first. Compare values when both nodes exist, then recursively verify left and right. Both sides must agree for the overall result to be true. We translated that plan directly and ran it on LeetCode, clean execution with no errors. We validated with examples. Identical trees return true. and differences in shape or values returned false, test cases passed as expected. The big lesson: recursion succeeds when base cases are exact and comparisons are symmetrical. Nail this pattern, and you're set up for problems like symmetric tree, subtree checks, and beyond.